Okay.
All right. Yep. So I can take it from
okay.
here. All right.
Thank you.
Well, thank you, David. So, well, the focus of let me just move this around. There you go. So the focus of the webinar is to explain a fundamental topic of the software that are the loads, okay? So I'll cover the listed topics using this presentation and some examples in the software, all right? So well, let me turn off my camera so we can focus on this presentation. Okay, so the first topic that I would like to talk about is when you're modeling a connection, what you see is this portion of the model. As you can see here, of course, that's the portion that you normally see in the model, all right? However, behind the scenes, we have a larger element. Those are called condensed superelements. This element is added behind the member end and has the same properties as the elastic shell model of the member, that it's this area that I am putting here in the presentation. So it is just one element, but it allows any elastic deformation and stress to develop in the member ends. That is again the visible shell model. All right. So you can see from this picture that this was added from version 21. And with this new formulation, we got better compliance with experimental tests and design codes. Again, we got accurate stress strain and deformation of members and in the main model that we are focusing in. I'll put this presentation in the website of the webinar so you can go to this knowledge-based article of IDEA StatiCa to learn more about this condensed superelement. All right. But okay, so to explain why this is important, I'll use this slide. So here you can see the condensed superelement in red and the visible shell model. All right. So this is the model that that we normally see in IDEA StatiCa. So the length of the visible shell member is always 1.25 times the height of the cross section from the last operation. So you can see that this line is starting from this shear plate, all right? And then if you start adding another operation, for instance, a stiffener, so that will start from that stiffener. So that length that I am mentioning here. From the end of the visible model, the condensed superelement is 4 times the cross section. So again, why these lengths are important? Well, those values are important to load the model. Why? Because IDEA StatiCa uses moments to load your model. For instance, from the shear force you input, we calculate the moments created by that shear force and use it to load and deform the visible shell model, and then get the strain and the stresses from it. Then we got the results. I mean, we got forces, and then we compare those against, for instance, AISC formulas, right? But that is why always we show this moment diagram that you're seeing here, okay? Because this is how you will, well, this is how IDEA StatiCa will load this member. So how you can bring that moment diagram, this is important. Also, I'll talk about more about this moment diagram later, but the moment diagram on the model is just for the visible portion, all right? So you can see the value and the diagram when clicking over wireframe view, then you click over the load effects, and finally in the load effects table, you click over the members. So then you can see this moment diagram created by that shear force or by the input of moments that you input over here, okay? So sometimes our users ask why we are showing the moment diagram. Well, one is to show how we load the model, and the other thing is to consider that even though you just put a shear force, a moment is on that beam. So let me explain you this with this example. So I model this frame in a structural software where you can analyze 2D or 3D structures, all right? And I did a simple frame with this beam over here. I put, I release the moments for that beam, and I input an uniform load to this element, all right? So moments are released. And then once you put the shear force diagram or shear force results, this is what you get as shear force diagram. So that is the shear force you input in BC for for loading your connection. Let's say you want to analyze a connection from this beam to this column. So this is the value you will input there in IDEA StatiCa. Why? Because this is the end force of this member, right? But once you turn on the moments results and you show that, as this is a pin joint, the moments are 0 at the start of this member and at the end, right? But the moment forces starts to develop from the start to the beam, and the maximum moment will be at the center of this member, right? So that is why IDEA StatiCa is showing this moment in that member, because we are not focusing just in this tiny node over here. We are like taking a photo of this frame, right? And we are focusing in this area. So you can see that over here. So I did this example. I mean, you can also do this example in IDEA StatiCa. Just make sure you select the same member that you're testing in your structural software, and then you can start getting results from it. So again, this is like taking a photo of this area, all right? And this is the moment we are showing over here. Okay, at certain distance, that is the moment you get in that member, created by the shear force that you input over here. All right. So when I am showing the model in the software, I'll show you a trick to know what is the real length of that visible shell member if you want to do like hand calculations and calculating the moment that we are putting here in IDEA StatiCa as well, right? So hopefully you understand why we have that, and if not, you can just put the question there. I'll have time to answer some questions at the end. Well, with that explanation of from where the moment comes, then another important thing is that in this case, this connection, this beam to column connection, it is from the center point of this column and the center point of this beam. So we normally don't model the offsets in your global analysis, right? Sometimes you do, but sometimes, well, the majority of the times we don't do that. So because of that, then we have this load position input in IDEA StatiCa, because when you're doing a connection design, we're focusing on that joint, and then here the offsets are important, all right? So load position is one of the key boundary conditions of the software, as it indicates where to locate the force. Okay, so this input needs attention when the member only has shear forces. Okay, this will indicate the distance along the member to place a shear force. Also, you indicate where the inflection point in the bending moment diagram will be located. As you can see here, in this case, the red line is representing the shear force that I'll input in this model, right? And then using the load position, I am also indicating the software where that hinge will be located. So that means the inflection point of this moment diagram that I am showing here. Okay, and that you can see in the software. So again, or well, this list is representing like the key points of the load position input. This is the distance along the member to place a shear force, and always it is taken from the start of the member. By default, the member starting point is on the node, unless you modify the EX offset. So I'll show you also that in the software. As I mentioned, it indicates the inflection point in the moment diagram. That means the hinge, and each member has its own load position input. So I am always recommending to double check the load position input, because this is one of, well, this can affect the results in your model, right? So let's explain the three options that you have in IDEA StatiCa to locate this force, okay? So the first option is the node. So that means it is on the starting point of the member, usually at the node, unless you modify the EX offset. Again, if you modify that EX offset, you're modifying the starting point. So that will be from the starting point of the member. Then we have the bolts option, and that will be valid when an operation contains bolts. For instance, shear plate, plate angle, or maybe an end plate, all right? So with that option, you are telling the software to locate the shear force where that bolt is located. In this case, at this position, as you can see this line. And finally, we have an option to indicate that position, but you will need to input that distance. Again, that is taken from the start point of the member, okay? I'll show you in the software that sometimes maybe the bolts option doesn't work, so you need to use the position option and input that distance there in the software. I mean, one of the advantages of having this input is that you can assess that shear force in different positions in the model, right? Rather than being a complicated thing in IDEA StatiCa, I see this as an advantage, because maybe you want to assess that shear force in the well line, in the face of the column, in the bolt's position, or at the end of this welded plate, right? So this is one of the advantages of having this position input. So let's jump into the software with some examples that I have. These are simple examples, but well, well, I can explain better with those. Then you can learn from it and make it correctly in more complicated models, right? So let me bring this model over here. Okay, so this is a shear connection, right? Where you want to let's modify, let's say 20 kips, and you come to this B member. Remember, all the members has its own forces in input or load position, and then you say, okay, I'll locate this into the bolts. So how you see that this is really working? Again, go to wireframe view, go to load effects, and then click over that member that you want to see the moment diagram. So now you can assess that, well, you can be sure that the load position is at the bolt's position, all right? But what happens if you say, okay, I am going to change the type of connection to welded, and then go back to load effects and wireframe view? Then it is well, the load position is at the node, even though I put forces in bolts. Again, this is valid just when you have bolts in this operation. So for that, you will need to use position, Okay, input the distance from the starting point, and then you will have that. Then you go back to load effects, click over the member, and now you can see where you're locating that shear force. All right. So it is always mandatory to come to wireframe view, see the diagram, and see if the load position is okay or where you are expecting. All right. Then let's jump into this connection here that I have. And let's say you go to B1, you're sure that you just have shear forces and you want to assess this shear force at the bolts position. So you come here and say, okay, forces in bolts, you run the analysis and you get auth deformations. So you go back to load effects to double check that you have the wireframe view. And then you see that the bolts position didn't work, right? Again, so sometimes the operations that contains, well, this operation contains bolts, for instance, the CPL2, but it didn't work well with that bolt option. So then again, you will need to go and change it to forces in, okay? So you go back here and now you have it there in that bolts position. And what I am telling you that this is important just when you have shear forces. Well, let's jump into this example. And for this case, you just have axial forces in these two bracing elements, right? So if I change this, and then I go to load effects, it doesn't make any change, right? If I go again to D1 and change it to node, it doesn't make any change in the model or the moment diagram. Why? Because this axial force is not creating a moment. It is not creating a moment diagram over there. It is only important when you come and put, let's say, -2 keeps over here, and then you have this moment diagram. And then in this case, you should move that load position to the area where you have these bolts, because you want to assess that hinge over here in the most weak area of the connection. All right. And of course, you can test it as well at the weld area, but that's why this is important for the assessment of this model. And then the last thing about load position, let me move this. Let me turn off the clit operation. And you say, okay, you start with this connection, right? And you say, okay, I'll add an offset here because my connection starts from the face of the column. Let's say, so this is 16, so you put 8 inches over here. So then you add the operation, and then the operation do the cuts and everything. So it is okay. So you don't worry about that. But then you go into the load effects again, and then that hinge is moved. Why? Because as I said, if you modify the offset EX, you're modifying the starting point of this B member, so that load position will be taken from the starting point of this member, right? So that's why you have it over here, because it started from the face of the column. So this is important. I mean, this is important because it can modify completely a model, right? Make sure you verify the forces position when you just have shear forces in the member for every member in your model. All right. The other thing that I would like to show you here, let me delete the offset, put it 0, okay, and put this into the node. So you remember that screenshot that I have when I was doing that moment diagram from other structural software, right? So the way to know what is the length of the visible member, I mean, you can use the 1.25 times the height of this cross section and do the maths, right? But a quicker way to do this is that you add a -1 shear force, okay, in this member, and then you will have here this moment. So this moment, it is, let's say, translated into the length of this member, right? Because the moment that we calculate is shear force multiplied by the length of this visible member. So in this case, we have 24 inches because I have keep inches as the as the settings that I have here for the moments. So this is how you can know what is the length of the visible member. All right, so that was like a trick. All right, let's go back to the presentation to continue with this. Okay, so the next topic is loads in equilibrium. Okay, so loads in equilibrium is the way that IDEA StatiCa allows you to input internal forces to the support member. If that option is toggled on, in the load case input, you will see the end and the start of the support member available to input a load. Also, that means that IDEA will indicate if the joint has equilibrium or not. That can be seen in the unbalanced forces table. So you can see this option here. This is on, toggle on, and then you will see this table of unbalanced forces. Okay, so this is like the statics check of this joint. This option, I mean the loads in equilibrium option, is activated by default, but you can unselect it, and that will fix your support member at both ends if that member is continuous. Okay, so you know that every member can be either ended or continuous, and in this case, if it's continuous, that will fix both ends. Okay, having loads in equilibrium is the safest approach, but I know that some cases we don't have the full picture and you don't have the internal forces. So that is why we have both options. Remember that engineering judgment is needed in every input of IDEA StatiCa. Finally, there are some cases that probably you have some unbalanced forces. I'll show you an example in the software that do not affect that much the model, right? So those unbalanced forces are always taken by the support member. And if the support member is okay with that rotation or extra forces, that is fine. But again, all is about engineering judgment, all right? So let me jump into the next slide about loads as percentage of member capacity. So IDEA has this option to, instead of inputting forces as kips or kips feet, you can put a percentage. So that will means that you're loading your model in terms of the member capacity. Okay. So for instance, here you input for M2 and M3 50% of the actual capacity of that member. And in the model here graphically, you will see the actual force shown in kips. Okay. So that is kind of useful because sometimes I know that you're given just the percentage of the load that that connection needs to handle. I know that it is not 100% correct, but we have this option if you want to use it, all right? So for that, you can activate this small icon that I have. I'll show you in the software later. Here you can see the percentage icon, okay? So you activate that and you will have this input as percentage here, all right? So we use these formulas for, well, to calculate the capacity of the member. For the moments we use the plastic modulus, okay? And well, you can see here the formulas for LRFD. So this is the material factor, and this is ASD. In this case, you need to divide that. So if you want to just double check these values, we use these formulas over here. Okay. All right, so let's jump into the two examples that I have. This just are like visual examples. Okay. Okay, let me bring this back. All right, so this is a model, an end of a truss. So this member is ended, right? And let me show you what is the design of this connection. So you can see we have two plates over there. But this is not a modeling webinar. It is just to explain some things here. So for instance, in this case, you come and say, okay, I'll analyze this connection for 20% of its actual capacity for both members. I don't care what size it is. I just want to assess this using that 20% for actual capacity of the member. So you can see here all the unbalanced forces because the loads in equilibrium is active. Okay, so we have huge unbalanced forces in this node, of course. And then you analyze the model and you see, let me turn on the form shape over here. Okay, so you can see here that, wait a sec. So you can see here that, well, the plate is okay. We are not having any critical things in the bolts, but the worst part of this model is this column. Of course, because, well, you're just analyzing for random loads. You cannot come and analyze this by percentages, some random, percentages. So the best way is to get the real forces, right? And analyze this connection to the real forces that you will get. But again, this is to demonstrate that the unbalanced forces are always taken by the support member, in this case, this column, okay? So even though we have that option to use the percentage of member capacity, it is not the recommended way to analyze a connection, okay? And then let me show you this. So this is like the recommended way. Having all the forces, let me go back to solid view so you can see. So all the forces in the support member, this is a support member. Here we have just one support end, okay? Having all that information. Of course, this is an example that we import from other software through checkbot. So that is the best way. Even though we have some unbalanced forces, I mean, that is acceptable. And you're assessing if that support member will handle those unbalanced forces. And then you go to the check tab and see the stresses here. Let me put it in here. And then you can start like optimizing this connection, maybe increasing the thickness of this plate or adding more bolts or whatever. But I mean, you also are accessing the support member. If you see here, let me put it in the form way. So this member is it's almost, well, you have some hotspots over here, but then you are in the safe side, right, of designing this connection. Because if you turn off loads in equilibrium, this is stiffer at the end, at the start. So you have a stiffer member, and that won't be a real result of the connection. All right. So it is always preferred to have all the loads coming from your structural software, or at least real values coming from an analysis. Okay. All right. So let's go to the last topic in this webinar. This is about importing loads combination from Excel. Well, we have, as you know, or if you don't know, we have a lot of links with other softwares to import load combinations and load cases. We have a webinar about this topic that you can look into our website or our YouTube channel, where I explain the process to bring information from other software. But there are some softwares that we don't have a link, or maybe you just want to analyze one joint from one model and you want to bring the real information or the load combinations from that software. So this is why we have this option as well. Okay. The best is to use checkbot, of course, because it is an automatic process. You don't have to data process like I am going to do it here, but I mean, we have this option as well. Okay, so this is like a recommended process that I did. It is not the only way, but this is one recommended process. All right, so I did an example with a Risa model, okay, that I am doing this example because I know we have a lot of users that use Risa, and as now we cannot import, it is not on us, but we cannot import the forces from Risa, just the geometry. So I found this option of importing loads through Excel very useful. So the first step, as you can see here, is to match the IDEA member's name to the other software naming conventions. So you can see here the naming, the number of the members over there. So let me just show you my model over here. Okay, so I match the names over there. And then the second step is to click over XLS export. So that icon is in the software. Let me show you where is that. Okay, so you will see here. So the first step, the second step is to click over there, and then IDEA StatiCa will export the template. So you can use that template to input the forces from the other software and then follow the next steps. Let me show you. So this is what IDEA exported. So this is a way to know how IDEA requires the forces to be imported in IDEA StatiCa, right? This is the beam name because I changed that name in IDEA StatiCa. And then, as you can see here, the third step is use the template provided by IDEA. Then you go to the fourth step, that is data process in Excel to match the local axis. Okay, So in Risa, let me go back here. In Risa, I can export the forces to Excel from those selected members. You use the filter out option, you export the data, and this is what I got from Risa. Let me show you here. This is that big list. From Risa, I got this raw data, right? And for every member and for every load case, well, for every member that I select, and you get the results for every load case at the end and at the start and at the end of the member. So these are the member and forces, okay? But I just need one result, right, from the 72 member. So in that case, I come here, I activate the end view, well, the colors, to know what is the nth portion that I need, okay? Then what I did here in my Excel sheet is to arrange this as IDEA needed. So this is load combination 1, load combination 2, load combination 3, and so on. And then for each member, I put what is the nth node that I need, right? I just need 174J nth force, 73I, and M72J, right? I put an unique name using this formula in Excel, right? And I do the same with this unique name. And then here, what I am doing is I am using the VLOOKUP formula and match the local axis forces from Risa to IDEA StatiCa, right? Why? Because, for instance, the moment at the let's say the stronger axis of the beam for Risa is moment CC, and for IDEA StatiCa is on MY, right? So I have to range the data as IDEA is requesting it. So that's why I'm using this VLOOKUP formula. Once I arrange this data, and I did everything here, I go to the Risa model, sorry, to the IDEA StatiCa model, and I use this option that says XLS import, okay? I go back to my Excel, select just the number values, okay? Control C, go back to the model, and I click over here just in the values, well, when it starts in the axial force, and Control V. Okay, and now I am pasting this as IDEA needed. Axial force By, Bc, Mx, My, and Mc. Okay, then you have this option to just import the load, only the extreme values or the extreme load effects. So IDEA filter out the worst cases based on the worst positive axial force, the worst negative axial force, and then it does the same for all this type of forces. Okay, so you can select import only extremes. If you want to import everything, you just well, you don't select this option. I can click over here, replace existing loads, and I click OK. And then I got all the load effects over here. Okay, so I mean, it is not as straightforward as doing this with checkbot, but this helps you a lot or save a lot of time. All right. What else? Yeah, I believe that's it from this process. I'll upload that Excel if you want to see the formulas that I use in the website of the webinar, so you can use this as a template, but this always will change. So you will need to follow the process that I did to have your own table. All right. And well, I use Risa in this case, but you can use whatever software you're using and find the way, well, the more like the faster way to arrange the data as IDEA needed here. All right. All right. So I believe we have some questions, isn't it, John? So we can jump into the questions.
Awesome. Thanks a lot, Andrea. Yeah, we have only a few, but if anyone has more questions, please feel free to ask them in the chat. So a few things regarding the length of the member. So just to confirm, you are able to change the length of the member shown in IDEA StatiCa, which is usually shown as 1.25 times the height of the material, right? And that 1.25, is that something that you can change?
Yeah, you can, let me go back to this so I can explain you over here. This is something you can modify in code setup if you want to increase that length. But as I show you, that condensed super element is creating a larger element, so we got accurate results from well, with help of that condensed super element. But yeah, anyway, you can modify that here. Let me just show you in this. Oh, I have to reset. There you go, here.
Yes, excellent. And the second part of that question was whether we were able to change the length of the super member, and I believe we cannot do that, correct?
No,
oh, yeah,
we can. Yeah.
Excellent. I think was a question regarding why it is necessary to determine the position of the loads. So there were a few questions about this, and a big reason why we do not force the location of the loads in IDEA StatiCa, and we prefer to give you the opportunity to actually define where the load is positioned, is that it really depends on the assumptions made in the main model, and there is no one great answer whether the load has to be in the bolts or in the welds or somewhere else. It really depends on the assumptions. So we just want to give you the opportunity to select that based on your actual elements.
And just adding a thing over there, we have some verifications from university, for instance, the ones that the University of Tennessee is doing, where they assess the different locations of that hinge. So if you're interested, you can go into our website and you will see the assess of the different location of the forces. So, I mean, if you want to see that difference. All right.
Awesome. And then there's been a few questions about the link with Risa 3D. And just to reiterate, we would love for the loads to be able to be imported from Risa to IDEA StatiCa. Unfortunately, at this time, it is on Risa to work on this export and for them to allow for imperial units to be transferred to IDEA through their SAF file format. So any Risa 3D user, feel free to ask Risa to potentially work on it. We're trying to ask them, but this time that's not something that we know as being ready in the pipeline, at least, unfortunately. So currently it's only the geometry that can be exported from Risa to IDEA StatiCa. And then I'm getting to questions that are just coming in, so I haven't had the time to read them yet. Is it possible to create any kind of model? For example, can 3D models be imported? And that's correct. We have integrations with many different software, for example, RAM structural system. and you can bring in the entire model into IDEA StatiCa. A few other questions about whether the webinar will be posted, the recording will be posted on the website, and yes, that should be done either today or tomorrow. You'll have the full recording of it. And Dave, if you see any other question also that you would like to answer, let me know while I'm reading them as well. How can you control which members take the unbalanced loads? So the red square. Andrea, do you want to take this one?
Yeah, so you cannot control that. I mean, that will be always on the support member. But I mean, you can set with which is going to be your support member. Okay, so if you right click over the member, then you set up that. Like if you want to change it to the B member, in this case, it won't be like correct, but you can set bearing member here.
Awesome. An important question. When imported, the forces are from the structural analysis are always at the node. So if I put them into IDEA with a position way, is that valid? Or can I take into account the position of each load coming from the structural analysis? So is that something that you can define while importing loads in through checkbot, where that load is being applied?
Not in checkbot, but when you open the connection. So when you open the connection, you can move the position of the load, because
okay.
every member will have that option over here.
Okay. Regarding the export from Risa through Excel, for the manual load input via Excel from Risa, did you determine that the position, that the positive or negative direction of the forces are consistent between Risa and IDEA StatiCa?
Yeah, well, you'll need to double check that. I double check for this particular model, but I believe it has some lateral loads. So then, I mean, that's something you will need to double check. I cannot tell you like this will be always okay or not.
Right.
Yeah.
Yeah. So that's something that you need to take a look at and confirm without trusting it blindly, I guess. Questions about the analysis. If the analysis comes up less than 100%, any tips to get it to 100%? The quick answer for this is there's no tip. It just means that there is some instability at some point. I believe in the one that you're showing currently, Andrea, you ask the software to stop at the limit strain. So that gives you some more understanding of the limiting factor. For example, here, the welds are the ones that are the closest to 100% capacity. So that's a good way to have a step-by-step process of increasing the welds or increasing the number of bolts one by one until you get something to work. But there is no one tip. It's really about specific connections, I guess. Is there anything you want to add to this, Andrea?
No, yeah, that's what you say. That is the answer.
Is it possible to modify load properties such as name in a tabular way? You can change the name of the load effects in IDEA, and like there you go.
Yeah, from here, but yeah, well, I already submit a request, so when you're importing that, you can put it your own name as well.
Correct.
Yeah, yeah.
Could we assume that a shear considered at the node is more conservative than an additional moment that is induced in the offset connection? That could be more conservative. It really would depend on the actual model, I guess, but depending on the forces and how the different forces interact with each other, there is a chance, I guess, that shear could be more conservative than some moments.
Yeah, I believe so.
I don't know if we'll get an answer for this one, but let's try. What about the minimum forces in members based on probable capacity of the member when designing for seismic provision of steel code. So minimum forces in the seismic design, in the capacity design analysis tool. I believe we only check the connection for full moment capacity, so that would be the maximum moment. I'm not aware of any need for minimum forces, but I'm not well versed in seismic design. I guess we can take a look at this and come back to you at a later time.
Yeah.
Is it possible to import an IFC into IDEA? At this time, I don't believe we can. David, let me know if that's incorrect, but I believe that's something that we would like to be able to export to in the future. Go from IDEA to IFC, which is a pretty commonly used file format. But at this time, I don't believe we have that capability. Correct, Dave?
Correct. And part of the reason that we don't have an IFC is that, depending on what software is producing that IFC, it's not necessarily that the same amount of information is included in each file. Some software go much further and add more information into the IFC, whereas others are relatively basic. So that's a tough one to kind of select when we're working with steel connections. So at this point, no, we don't have the opportunity. We don't have the ability to import it.
There is a question. When you were showing the Excel workflow with Risa, Andrea, what was the purpose reason for the unique name that was created?
That is because the reason was to use this VLOOKUP formula in Excel. So in this is the IDEA, let's say, template. Let me rename it here. IDEA template, right? So I just need the result for the end of M64J, right? Load case 1 for this value. And in the Risa results for that member, I have 2 results. So then I will have 2 results for that 64. So the cell that I am looking for is the 64G. So with that VLOOKUP, then I look in this unique name column, and then I use this value to copy on the IDEA template. Yeah, basically that it's for the formula of Excel. Yep.
Awesome. And actually going back to the question that was asked just before about the location of the shear force and whether it would be more conservative, there's a bit more precision. So the user was asking whether it could be more conservative to have the shear at the node rather than having the shear in the bolts, for example, in a shear plate connection like the one that you're showing here. Whether having shear in the node of the column would be more conservative, could be more conservative than having the shear in the bolts. And yes, that's very true. Could be more conservative, but it could also be wrong because you would be inducing some moment in the welds and in the bolts here in the shear plate. So that's definitely something to look out for, but it could be conservative by a good amount. And another impact of this as well is that if you were to run the analysis shown here, for example, with vertical shear only, but that shear being applied at the center line of the column, that induced moment in the beam, when you go to the check tab and look at the deformed shape, you could see the beam actually moving upwards for a vertical load, for a gravity load, so vertical load going down. So that could tell you that something is actually off with the way the analysis was run. So it could be more conservative, but it could also be plainly wrong, depending on the scenario, of course.
Yeah, I am modeling this, but yeah, that will take time.
How is taken the condensed super element length in prismatic members, so members that have a variable height? That's something that I'm not aware of. I think it would be the highest. Like,
yeah, but the variable, we don't have variable members. I mean, you can add more parts to that variable. I mean, you can increase it using another thing, but we don't have variable members.
Okay, that's a good point.
Variable height member. Yeah.
We're getting to the end of the questions. If anyone wants to add a few last questions, feel free. Right, and someone just commented as well on what we were discussing before. If the connection is a moment connection, adding the shear force at the node creates counter moment, which might make the connection safe, but it's actually not. That's a good point, exactly. I agree with this.
Yeah, but maybe I didn't talk about, but what if I add a moment over here, right? And then move that. So that moment is also added into this moment diagram. Of course, you have it here. All right.
But what if that's negative, does that then?
I am putting the forces in in the node, so that is why. If I put it here and go back, there you go. All right.
Okay. Do you want to put up the last slide? We're coming up to 1 p.m. So the other questions I know there have been a couple of more questions that came in the last minute or so. We will send you we'll email the answers to those to you. Just wanted to kind of mention before we sign off here for the day, the next webinars that we're going to be doing. So the next one will be May 3rd, and that will be what's new in version 23, kind of focusing more on the US AISC enhancements that are being made, including some pre-qualified moment connections for seismic design, kind of per AISC 358. Then we're going to kind of doubling up in May, just because of when version 23 is coming out at the end of April. And then at the end of May, we'll be giving a presentation on stiffness analysis. And then one last thing is just if anyone's going to be in Charlotte for the Steel Conference in 2 weeks, definitely feel free to come by the booth. We'll all be there, and look forward to meeting everyone. Our booth number is 1636. So definitely, feel free to stop by and bring your questions. So I think with that, we're at 1 o'clock right now. So we're going to go ahead and shut it down. Thank you for attending, and we will talk to you in about a month. Bye.
Thank you. Bye-bye.